Okay, let's take a look at this week's material where we are going to use tidy models to compare different models. Um, so most of my content comes directly from the Tidy Modeling with R textbook. We're going to look at chapters 9 through 13, and this there's quite a bit of stuff going on here. So please do make sure you do your reading and and also refer to the different documentation here. Okay, so first things first, we got to load all of our packages. So we're going to load Tidyverse and Tidy Models, and when you do that, R lets you know that it's loaded up a bunch of stuff. Okay, we're also going to work with the Ames housing data set, okay? And just a few kind of things that we've done at first is we've transformed the sale price to be logarithmic. So we used mutate and we reset the sale price to be log base 10 of sale price. We also are going to split the total data into a training and testing split. So we use the function initial split. We're going to keep 80% for training, and the remaining 20% will be set as testing. And once we create that initial split, we will extract the training portion and the testing portion from that and store those as Ames train and Ames test. This is the recipe that we created last week. Okay, so we begin our recipe with saying that we are trying to predict sale price based on these variables. The variables are neighborhood, ground living area, the year it was built, the building type, latitude, and longitude. Neighborhood is a nominal variable. Building type is also a nominal variable. The others are numeric. We're going to take ground living area and we will apply a step, a log, to convert ground living area to a log scale value. We are going to take the neighborhood variable, which is categorical, and we're going to create a other category with a threshold of 1%. So basically categories that appear in the neighborhood. So neighborhoods that just don't show up very often in the data, less than 1%, will just get thrown into an other. Then we will make dummy variables out of the neighborhood category. That picks one of the neighborhoods to be a baseline, and then it creates ones for basically all of the other things, ones and zeros. Same thing with building type, because that is also a nominal predictor. We're also going to create interaction terms by using step interact, and we're going to look at the interaction between ground living area and building type, because what we saw last week was that for single family homes and a lot of other property types or building types, as the ground living area gets bigger, the value of the sale price goes up. But there were some things like the duplex where even though the ground living area got larger, the sale price did not increase. So we wanted to kind of include that possibility with the interaction term. And then lastly, we want to have a nonlinear relationship between latitude, longitude, and the sale price. And so what we're going to do is we are going to convert latitude and longitude into, we're going to apply a spline function. So we're going to use step ns, which will create a natural spline. And what we saw last week during the creation of our recipe, just kind of eyeballing it, we chose to use 20 degrees of freedom for defining the natural spline of latitude and longitude. Okay, and so this is just kind of the list of what we've done in that recipe. Also, what we did last week is we created our first kind of model and workflow. Our model we specified to be a linear regression model. We set the engine to be LM, which is a function in base R. And then we threw that into a workflow. So we have the LM workflow where we start off with an empty workflow, which is an object created by Tidy Models, and then we added the model. We did add model, and we added the recipe, which we had defined. And we're going to fit this workflow to our training data. So we called fit the LM workflow, and we apply it to the AIMS training data, and there we fit it. So this is what we did. We create the model. Linear regression, we use base R's LM engine. We create the workflow by adding the model and the recipe, and then we fit the workflow to the training data. So what are we going to do now? What we want to do now is we want to kind of take that model and we want to measure its performance. So in machine learning, the way we do this is we use the model's ability to make predictions. This is kind of how we evaluate the model. So rather than the classical approach that you might have learned in 101A, where you do regression and you look at the summary table of coefficients and see if those things are significant or not, and you check your assumptions, in machine learning, for better or worse, our evaluation is less concerned about the probability model or the mathematical assumptions that are being placed on the data. So, for example, even if the linear model displays something like non-constant variance, okay, if our predictions have good performance, we might still choose to use the model, even if it's clear that our assumptions are wrong. So this is kind of the machine learning approach. We just really care about our predictive performance. And Chapter 9 is all about measuring that performance. A large portion of Chapter 9 is spent on measuring performance for classification models, which is also important. But we'll come back to those when we cover classification. Right now, we're still going to focus on regression. So what we're going to do is we're going to make predictions using the fit. Okay, we call predict LM fit, and we're going to provide the new data, which is just our test data, where we've removed sale price. Okay, so we're going to have we're going to predict called predict on LM fit. We'll store that as our AIMS test results, and AIMS test results produces this column, which is basically all of our predictions for our data. And what we can do is we can bind the original sale price to our predictions. And so we will call bind columns. We'll take our test results, which just had this one column of dot prediction, and we are going to bind basically from this AIMS test data that column sale price. Okay, and so here we get differences. These are all in log 10 units. Okay, so a difference of 0.05 and 0.02 is you got to raise, you got to do 10 to the 5.07 and 10 to the 5.02 to kind of get what the actual difference is. But here we can plot the actual sale price versus the predicted sale price. And we see, overall, we have a pretty decent fit between the predicted values and the actual values, okay? Perfect fit would be right along this diagonal line. We've got a little bit of scatter, okay? And it seems that when the sale price is low, we tend to overestimate, and when the actual sale price is high, we tend to underestimate. But overall, in kind of this middle-ish range from 5.0 to 5.5, we seem to be getting pretty good performance. We can calculate the RMSE, at least for our log thing. Okay, so we'll call this function RMSE. We take the AIMS test results, which have these two columns, dot prediction and sale price. So this is, remember what we've done is we've built up AIMS test results as a tibble with two columns, and the RMSE function takes in two arguments: the truth, which is going to be the actual value, sale price, and then our prediction is going to be the estimate. Estimate is going to be our column dot prediction. And when you do that, you measure the RMSE and you get a 0.0736. If you want, you can also get more metrics. So you can create a metric set. This is kind of like a little vector of metric names, but we call metric set. So you can do something like the RMSE, root mean squared error, R squared value. Okay, MAE is mean absolute error, or is it median absolute error? Either I want to say mean or median absolute error. So you're taking basically the absolute values of the errors, and you're calculating. I want to say the median, but I could be wrong about what the M there stands for. Okay, so these are the different metrics, and again, you just call. So this is metric set, okay, and then once you have the metric set, okay, then you put in the data, okay, with the actual values, the test results. You specify the column for truth and estimate, and it will spit out the values. Okay, obviously you can't compare RMSE with R squared or MAE. These are just three different measures of performance, predictive performance for this particular model. And what we would do is we would have a competing model, a different model, and we would have it make predictions, and we would gather the metrics for the competing model, and we would compare these metrics with the metrics of the competing model to try to decide which model we should use. Okay, so model metrics for one model alone is not very useful. Model metrics are useful when making comparisons between multiple models. Okay, so again, just like any other kind of summary statistic, the GPA of one student by themselves is not going to be incredibly useful. Okay, but if you have the GPA of multiple students, then you can use that to make comparisons. Okay, and again, something like R squared or root mean squared error is just a summary value and doesn't tell the entire story. However, it is a useful metric. Okay, and so that's what we try to do. So here we're going to create another model. Okay, another model for regression. This is going to be a random forest model. And we're going to use it to compare it against our linear regression model. Now, I have not yet explained how a random forest model works, but that I guess that will come later. But all that's important right now is that we can use a random forest model to make numeric or categorical predictions. Okay, and right now what we're going to do is we're going to have the random forest model make numeric predictions for the log of sale price. So what we're going to do is we're just going to establish the model and the workflow, okay? And that's what we have here. So our random forest model, we're going to specify as a random forest. This is something from Parsnip. This is in Parsnip. If you want a random forest model, you call rand_forest. You can put in a few options. So in random forest, you can say how many trees you want in your forest. You can set your engine. There's a few different engines there. One engine is random forest, but another engine is Ranger, which has pretty good performance. I guess you can think of it as a forest ranger. And so that's what Ranger does, has good performance. And the set mode is we're going to do regression. We're trying to predict a numeric thing. So random forests can be used to predict categorical or numeric values. In this case, we're predicting a numeric value. And so our mode is going to be regression. Okay. In order to use Ranger on your computer, you probably have to install the library. So, install.packages, Ranger, allow it to do the installation, and then you should be able to use the engine. And again, one of the beautiful things about Tidy Models and Parsnip is that we don't actually have to look up the documentation on Ranger to figure out how to use Ranger. I mean, using Ranger in of itself is not very difficult, but Tidy Models will automatically translate, our model and translate our desired instructions into what is needed to execute those commands in Ranger, and we don't have to learn the syntax for using that specific package. Okay. For the workflow, we're not going to add a recipe. We're going to just add a formula, and we'll add a model. We don't need to have a recipe because the way a random forest works is that it just partitions the data. So it just takes a variable and it just splits it, and we don't need to convert categorical variables into numbers, so we don't need to make dummy variables out of neighborhood or building type. Random forest will just say, hey, these categories go down on this side of the split, these categories go down on the other side of the split, so it can work with categorical variables directly. It also doesn't care if things are on a log scale or if they've been transformed with a spline or something like that, because all it does is it just says values that are bigger than this number goes on this side of the split, values that are smaller than this number go on the other side of the split. So as far as the random forest quote recipe, we just need the formula, which just says, hey, these are the variables we're going to use. So we're using the same variables: neighborhood, ground living area, year built, building type, latitude, longitude, and we're still trying to predict sale price. So that's going to be our workflow. And then what do we do with that workflow? We fit it to our training data. So we take our workflow and we call fit data equals Ames train, and that fits it to our data. Okay, and now that we have fit the random forest workflow to our training data, we will take those results. So after we've done this, so we have random forest fit. Okay, we're going to use that random forest fit to make predictions. So we're going to call predict random forest fit, and we're going to call it on the test data. Okay, we're going to say new data is Ames test, but we remove sale price, and that's going to create a column of predictions, a column dot predictions, and that's going to be Ames random forest test results. We also want to add the original column of sale price, so we're going to do bind columns Ames random forest test results, and what we're adding to binding the additional column is going to be Ames select sale price, and that's going to be Ames random forest test results. Okay, so at this point, Ames random forest test results, I didn't print it out on this slide, but it looks very much like this. Okay, so this is Ames test results for the linear regression, but Ames random forest test results looks very much like this, where we've created a column of predictions when we use predict, and then we're binding the original sale price column to that. Okay, so that's what we have here. And then I'm going to call RMSE. We want to get the RMSE on the random forest test results. Truth is sale price, estimate is dot prediction, and our RMSE is 0.0701. Okay, we can compare that to the RMSE of the linear regression model. Linear regression model's RMSE is 0.0736. Okay, so the root mean squared error for the random forest model is better than that of the linear regression model. Okay, and it doesn't seem like a huge difference, 0.0701 versus 0.0736, but keep in mind these are log 10, so it is kind of a significant difference, I would say. Okay, now we went through this process of going through and taking our models and running them on our tested data. Okay, now the truth is you should do this only once, all the way at the very, very, very end. Okay, so it is important to have predictive performance and evaluate that predictive performance, but using the test set should be done only once. Okay, and you don't want to have this back and forth between creating a model, measuring the performance on the test set, and then going back and refining that model and measuring the performance on the test set. Because if you do that, go back and forth with the test set too many times, then you run the risk of overfitting the test data. Okay, you run the risk of overfitting the test data. So what you want to do is you want to do something like cross-validation. So you take, remember we did our initial split between the training data and the test data. And what you want to do is you want to take the training data and then do cross-validation there. And you'll do cross-validation and you'll further split that training data into analysis and validation sets. Okay, and then you can kind of refine your models while doing cross-validation with the analysis and validation sets, and you'll try to say, all right, well, these are kind of my finalist models over here, and then with the finalist models, you test it out on your test data, and you say, all right, I think this one's the best one, okay? So that would give you kind of a preliminary estimate of your kind of model performance. So what we're going to do is we'll kind of redo our process here, but this time I'm going to create tenfold cross-validation. So we're going to do our AIMS training data. We call the function vfoldcv. I'm going to say I want 10 folds, and this will create AIMS folds. And AIMS folds is going to be kind of this big data structure that has basically different permutations of the data, where you have 10 different folds, each of them being kind of the whole training data, but just it's split 90%, 10% between assessment and validation. And then, okay. So we can set a few options to control how the cross-validation or the resampling will perform, okay? In order to do that, you can use the function control resamples, and that'll create a list that's used during the kind of fitting process, right? And so you can kind of look a little bit more, control aspects of the grid search process for how this is going to go, right? And as far as the control resamples, okay, you have a few arguments: verbose, allow, par, extract, save predictions, okay, and basically verbose is going to basically print a lot of kind of output, which is helpful, if when you first kind of fit your data, and if you run into problems and things like that, it will kind of output, as it's working through these things. Okay, extract is a function that you can run for retaining objects from each model iteration. Okay, and then save predictions, a logical for saving the assessment predictions and things like that. And so here we're going to kind of set our options to, we're going to say we want to save the predictions. We also want to save the workflow in our control resamples here. So that's another thing you can set here. Okay, a logical for whether the workflow should be appended to the output as an attribute. So it's just kind of, do you want to save that information? And here we're going to say, yeah, we do want to save that information, right? And so we're going to say keep our predictions. This is just an arbitrary name I'm creating for the controlled resamples object, which is how we're going to pass along these settings to when we do the vfold cross-validation. Okay, and so what we're going to do is we're going to fit the random forest workflow to the 10 folds of data. Okay, and with the control options, we're going to tell tidy models that we want to save the predictions and the workflows. Okay, so we use this function fit resamples. Okay, so we're going to do fit resamples, and this is similar. So when we first fit it, we did random forest fit. We took our random forest workflow and we just called fit. Okay, we're doing the same idea here. We take our random forest workflow, but we're going to call fit resamples. Okay, fit resamples, and rather than taking the original full training data, the AIMS train, we say fit it to the AIMS folds. The AIMS folds is the result of calling vfold cross-validation on the AIMS training data. Okay, so similar process, but instead of calling fit, we call fit resamples. And tidy models will then say, oh, okay, rather than just trying to fit it once to the training data, I'm going to fit it 10 times, once to each of the different folds of the data. Okay, and then the options that we want to specify as far as how the fit resamples goes comes with with the control argument, and we pass keep predictions, which is basically the result of control resamples. So this takes a few seconds to run. You're just seeing the output from my lecture slides, but on your computer when you run this, it takes a little bit of time. And so here we can say, all right, what are the results of my random forest here, right? So here I'm going to say the random forest results of the resamples. Okay, this is the results of 10-fold cross-validation. Okay, and so we can see each of these things. What it did is it fit on the assessment part, basically the 2,107 things, and then it evaluated against the 235. Okay, and when it does that, it calculates the metrics, and then it also, we told it to store the predictions, so it kept those as well. Right, and it did this 10 times. It said, all right, and then I fit it to the 2107. So it would be kind of like if you manually took 90% of Ames train and you got 2107, and you said fit to just these 2107. And then kind of like if I go back a few slides, after you fit it to those to that 90% here, then you say, all right, now I want you to make predictions on the remaining 10%. Okay, and then gather the metrics for the RMSE. Okay, and when you call fit resamples, it does that, and it does that automatically for you. It fits it to the 2107, and it makes predictions for the 235, and it calculates the metrics. Then it fits to the next 2107, makes predictions for the 235, and it calculates the metrics. Then it does it for the 2108, makes predictions for the 234, keeps the metrics, and it does it 10 times. So it really, really, really saves a lot of kind of tedious work that you have to do. You just call fit resamples, and Tidy Models does it for you. It's spectacular. Okay, if you really actually want to see the metrics yourselves, you can. So you can go RF resamples, and you can say, hey, I want to go into this metrics column, okay, the dot metrics column, and I want to see the first results, okay? And it says, yeah, you got 2 rows, 4 columns, and it says, sure, I kept the RMSE for, we got 0.0605, your R-squared value is 0.862. I kept these 2 things, okay? And then, so that was for the first, when it fit to these 2107, made predictions on these 235 observations. These were the results. Then we said, hey, do it again. Whoops. For this other split, these 2,107 and these 235 things. And when it did that, it got slightly worse performance. So the RMSE went up a little bit from 0.0605 to 0.0653. This was just a different set of predictions that it had to predict, and its prediction performance just wasn't as perfectly good. Okay, and we got that. The R-squared value just a teeny touch lower at 0.861. And again, it has it for all 10 different folds. You probably wouldn't bother checking every single one of these things, but it is, I would say, periodically as you're working through it, you should take a moment to just double check your dot metrics and things like that to just kind of make sure everything is looking reasonable because sometimes it's easy to make a mistake, and it's easy to just kind of keep following the process without ever kind of double checking along the way if things are kind of progressing as they are. And so if you see an R-squared value of like 1.0, all right, that would be kind of a little bit of a red flag that something is not quite right, because if you're getting 100% accurate prediction performance, you probably have like a variable that gives it away somewhere in your in your data, right? So things like an R-scored value of 1.0 would be a red flag that if you're predicting things perfectly, something is not quite right, right? Or an R-scored value that's extremely low, right? Like 0.02 or something like that. Also, probably something is going wrong, okay? But 0.86, that looks promising. That's what we have. And so anyway, rather than having to look at each entry in the dot metrics column, okay, each of these being its own little tibble here, you can call collect metrics. And when you call collect metrics, it takes the mean of all of the 10 things, okay? And so our mean RMSE is 0.0721. So here we got 0.0605 and 0.0653. Apparently some of these other folds, the prediction performance was even worse, and the average of the RMSE across all 10 folds is 0.0721, okay? And you can get the standard error. The standard error for RMSE is 0.003, so we expect, around 2/3 of them to be within one standard error. So what's that? 0.075 and 0.069. And then vast majority will be within 2 standard errors. So what do we have? Going up plus or minus 0.06. So this one's actually be more than 2 standard errors. So probably some skew here regarding the standard error of the RMSE. Similarly, for R-squared values, here we had an R-squared of 0.862, 0.861. Apparently, if you look at all 10 of them and you take the average across all 10 of them, you get an R-scored value of 0.831. So something's a bit lower, okay? If you wanted to, you can also go back and you can look at the predictions themselves, okay? So here, if I wanted to look at this first fold, I can look at the dot predictions and double square bracket 1, get the first tibble, and we would have the predictions for the 235 observations here. So here, if I say, random forest, resample results here, I've got dot predictions, okay? Double square bracket 1, we're just looking at the first one, and it says, all right, here is the prediction. This is the row that was randomly sampled, and the actual value of sale price was 5.09. So we predicted 5.1, the actual value is 5.09. We predicted 4.92, the actual value was 4.90, so on and so forth. And so we can measure exactly, what the difference is between dot prediction and sale price. Now that was already done for us, but if we really wanted to see ourselves what's going on, we can do this. And here we might identify, oh, here's an outlier. Here's something that's like really off, okay? And so for this one, we have 235 predictions, and we have one for every basically entry in that validation set. And then again, you can call collect predictions, okay? And what collect predictions will do is it will take all the predictions. It'll take the predictions from fold split number 1, split number 2, split number 3, split number 4, so on and so forth. It will collect all of them. And remember, when you do v-fold cross-validation, it takes the full data set, of which there were 2,342 observations. It takes that full thing and it partitions it into, in our case, 10 chunks. And here it's going to take all 10 of those predictions and kind of recreate the whole thing. So when you collect all of the predictions together, you recreate the whole entire data set, 2,342 observations, okay? Here they have the kind of the original sorting, which is, for fold 1, it randomly selected row 10, 27, 47, 52. If you wanted to, you could sort by the row to kind of recreate the original column of sale price. It will be identical to the original full training data, and then all, kind of their corresponding predictions. So we can see all of these entries here. And you can see these are the exact entries that were right here, right? 5.1 and 5.09, 4.92 and 4.9. those exact same things, 5.1 and 5.09, 4.92 and 4.9. And it's just, it has it for all of the folds. Right now we just have fold 01, but it will have, fold 02, fold 03, all the way up to fold 10. And so all of those things will have their predictions. Okay, so now that we can see how to run vfold cross-validation, we can use this process to then compare different models using cross-validation. So, here I'm going to propose 3 different recipes. Okay, so we're going to start off with a basic recipe, which takes our variables and makes dummy variables out of neighborhood. Okay, and also creates an other category. So that's going to be the basic one. Then we will add the interaction term, and that will be our interaction recipe. And then we will take latitude and longitude and make splines out of them, and that will be our spline recipe. And here, just arbitrarily, we've chosen 50 degrees of freedom for the spline recipe. But we're going to have basically 3 different recipes that we can use for the linear regression model. Okay, and then we will also still have the random forest model in there. Okay, so what we're going to do is we're going to create a workflow set. We're going to have different workflows here. And so one will be the list of the preprocessors, okay? And then we can provide a list of models, and then we can also do a cross between them. And so, so our preprocessors will be a list. We have the basic recipe, the interaction recipe, and the splines recipe. We give all of these things names because this is how Tidy Models is going to name each of the workflows. It's going to basically just combine the preprocessor, which is basically our recipe's name, along with our model name. So here we have basic, interact, splines as our names, and we're going to create a workflow set where our preprocessors is this list, okay? And then the models is also going to be a list, and here I just create the list directly in here because there's only one entry, but it's going to be a list where the model name is LM, and it's going to be our linear regression model. And then here we won't do all of the combinations of preprocessors and models because we just have one model, so it'll just get recycled. So we will have a basic LM, an interact LM, and a splines LM. And so we'll have 3 models there. If we wanted to, we could have where you have the recipes and the LM. So for example, instead of just a plain old LM model, I might create like something using GLMNet, okay, which I haven't discussed, but it's similar to LMs, and you can apply basically like ridge regression or lasso or something like that, just kind of some shrinkage formulas in there, and so you could put in like a list of LM versus and GLMNet. And then you'll have the basic LM, the interact LM, the splines LM, and then you'll have the basic GLMNet, the interact GLMNet, and the splines GLMNet. And a cross will kind of figure out every single possible combinations of the preprocessors and the models to create the workflows. Here we're not going to worry about that. We're just going to create a workflow set, and this will have basically our 3 workflows: the basic LM, the interact LM, and the splines LM, which is just a combination of each of these recipes along with the LM model. So that's our workflow set. We also want to throw into our workflow set our random forest. A little closer investigation into our workflow set. If you look at any one of these things, this will be the workflow itself. So if really, this first column is just the names: basic LM, interact LM, splines LM. And then right now we haven't fit any our workflow set to our data or anything like that. So our results are empty and our options are empty. But all of the information is stored in the info, and you can say, all right, well, let's investigate that. All right, and so we can say LM models $info, take that info column. I just want the first entry, and it says, okay, well, we have a workflow there. The preprocessor is a recipe, and our model is linear regression. And so we can say, okay, well, what's going on inside that workflow? Okay, so I do info double square bracket 1 workflow, and we can say, okay, this is our workflow, linear regression, and our preprocessor. Okay, this was the basic recipe that we created, which has step log, step other, and step dummy. And we can see those are the steps that appeared in this basic recipe. If we were to look at, say, the interaction recipe thing, we would see step interact thrown in there. If you wanted to kind of investigate that. I didn't create a slide for that, but if you wanted to, you could see that. So now that we have this workflow set, we would we'll call workflow map. Okay, workflow map takes a named function and runs it over all of the workflows in a given workflow set. Okay, so what we'll do is we'll take the LM models workflow set, which is this thing. We have our 3 workflows in the workflow set, and we'll put it inside workflow map. And then what we'll do is with workflow map, we're going to tell it we want to run fit resamples. Okay, we're going to run it, have it do fit resamples. Okay, so there's a few options. Seed is going to be an option for workflow map. And then verbose is another option for workflow map, and it's going to kind of provide logs of all of the activity. And so, so here we're going to remember fit resamples is kind of just like taking a workflow and fitting it to our training data, except we're not fitting it to our training data. We're going to say fit it to the vfold cross-validation folds. Okay, that's the resamples. So we're going to say fit resamples to our folded cross-validation. Okay, we give it to the set of cross-validation folds aims folds. We'll specify the resample control options, and that's all going to go in there. So here, I take all of our models, which is the workflow set with our 3 workflows. We call workflow map, and we say, hey, we want to run the function fit resamples. We give it a seed. We say verbose true. We're going to say the data that we want to fit it to, the resampled data, is aims folds, okay? And then keep predictions. These are the options that we've set for when we call fit resamples, okay? So this takes this takes a little while to fit, okay? Because remember, it's doing 10-fold cross-validation first for the workflow with the basic LM. Then it does 10-fold cross-validation for the workflow with the interact LM recipe workflow, I guess. And then we do 10-fold cross-validation, this time for each of the for the workflow with the splines in there. Okay, and that takes the longest. So so it does that, and it takes it finishes, okay? And so now we have the results, okay? So we have the results in here, which is stored in this column here for results. The options has the resamples along with the control, just information about that the workflow that was fit to the data, okay? So when I look at the results, so if I say LM models, we're going to look at results, and we'll just look at the first one. This will be for the basic LM, and we can see, hey, this is identical to the results of doing 10-fold cross-validation, right? So remember, I'm going back a few slides. So when we did 10-fold cross-validation on the random forest, these were the results, okay? We have resampling results, 10-fold cross-validation, Tibble 10 by 5, and we have the results right here, okay? Resampling results, 10-fold cross-validation, Tibble 10 by 5, same kind of results, except this is the results of fitting the basic LM. And I could check it for result 2, and it would give us the same kind of thing. They're all the resampled results here. And so here I can say, hey, collect the metrics on these results here. And so we've got the metrics, and we've got the mean RMSE for the basic LM, for the interaction LM, the splines LM, okay? and we also have R-scored values. And so we have 0.0803, 0.0799, 0.0785. So it does seem that the model with the splines has the best RMSE performance when we did cross-validation, and the adding interaction terms did improve performance, and over just kind of the basic LM. So it does show that things improve as we made our recipe more and more complicated. Okay, the R-scored values also go up from 0.791 to 0.793 to 0.800. Not a ton more, but as we added complexity to our recipe, that performance did improve. Okay, so also remember we created the random forest workflow, and we already ran fit resamples to that, and we stored those results as RF results. Okay, and so we can kind of take these results and kind of throw it in and compare it as part of our workflow sets. So one of the things is we can take those results, and we're going to use this function as workflow set, and then we'll kind of take all of those results and format it into a workflow set, and we're going to just give it the name random forest. Okay, random forest, and it has the info and the options and the results there. And then we can take this table and just bind it, okay, to all four models. So we have the LM models, okay, basic LM, interact LM, splines LM, and then remember we have random forest. So we took the results from random forest, and we're binding the rows, the other workflow sets. So now I have my workflow set. I've got 4 rows here. It's kind of interesting the way Tidy Models and the Tidyverse handles everything. It kind of treats everything as a table, okay? But each of these things can contain more tables, right? So this itself is a table, okay? But this in this quote cell, you know, for the row random forest and the column info, the contents of this itself is a table, okay? And then the contents of this quote cell here itself is a huge table, okay? It's actually a table of tables here. The results, it's this thing, okay? It's this table, and this thing, each row represents a different kind of fold of the cross-validation, and each row, you know, each of these things itself is a big table, right? So this is a tibble 2x4, and then the predictions is a big tibble with 235 rows. So, but it's just, you're just kind of like zooming out, and you have tables contained within tables, but you can treat them like tables in that you can kind of bind the rows and add columns and so on and so forth. So in our case, we had this table of results for the 3 different workflows that we did when we processed the workflow set. And then we took the random forest results, we turned it into a workflow set, which turns it into a row in this table, and we just kind of combined, we said bind those rows. And so now I have a table with 4 rows, 1 row for random forest, and 3 rows, 1 for each of the linear models here. All right, and so what do I want to do now? Well, one of the things is you can call an auto plot, and what that will do is it will basically look through the results here, okay? And in the results we have, within those results, remember we have basically the metrics, and we've collected those metrics and things like that. We can collect those metrics, and it will produce a plot. And so here we have a plot for RMSE, and so if I just go back here, we have 0.0803, 0.799, and 0.0785, and those get plotted right here. 0.0803, 0.799, and 0.07, I think 85 was it? Yeah, 0.0785. That gets plotted here. The standard error for each of these things, 0.00264, 0.00272, and 0.00282, get plotted as error bars here. And then we also have, let me just go back even more slides to our random forest results. Okay, our RMSE was 0.0721 with a standard error of 0.00305. Okay, and that's what we have over here, 0.0702 plotted right here, and standard errors of 0.0305. Okay, and so these are plotted right here. Okay, and it just says, hey, you know, the orange color, the pinkish orange salmon color, these correspond to linear regression models, and the green corresponds to a random forest. These ones all had recipes with the triangles, and this one was just a formula. And so this plots the RMSE values. And over here, we've plotted the R-squared values, and we can see, yeah, you have the highest R-squared values for the random forest and lowest RMSE for the random forest. And then as far as linear regression goes, it does seem like the models improve as our formula got more and more complicated. Okay, RMSE did go down as the it said the workflow rank. I don't know how it. Where did they go? Okay, well, I'm not sure how workflow rank got computed here, but we see, this seems to be the best performing model there. Okay, but yeah, certainly here these are pretty close and certainly within the error bars there. All right, this is a little bit, comparing resampled performance statistics. So this is all again chapter 11. So this is kind of a plot here that they did, and so they have additional information here. So it said, what did it say? Plot of the R-squared confidence intervals. We can see the random forest is doing the best job, and there are minor improvements as we added more recipe steps, and we can do kind of between model comparisons. All right. So information there, and more on this stuff. Let me see. So here you could actually see some of the different values as you resampled from the 10 different resamples itself. Let's see. It says, before making between model comparisons, it's important for us to discuss the within resample correlation for resampling statistics. Each model we measured with the same cross-validation folds and the results for the same resample tend to be similar. So here they're saying, okay, let's actually look at each of the, the 10 different folds and see how the performance changes. And so you can see for some of the folds, the R-squared value, like for this fold, everybody kind of performed pretty well as far as R-squared value. And then for this fold, there might have been just some outliers in this thing, and it was tough to make predictions. And so all of the models kind of performed poorly. Its R-squared values for these two folds didn't do great. Yet somehow for the random forest, kind of consistently improved for almost all of these things. This one particular fold in purple, okay, whatever predictions you had there, the random forest didn't do a good job of making predictions there for whatever reason. Okay, we don't really know, but here we can see, is there some kind of it says, if the resample effect was not real, meaning that it didn't really matter, the resamples, like some resamples, like some of the folds were tough to perform, and some of the folds were easy to predict, right? And because of that, you kind of see these consistent patterns here, where these lines, this line is near the top and stays up there, and these lines are near the bottom to indicate like this one was tough for everybody. Everybody kind of performed poorly. And so we kind of see these parallel features here, okay? And that indicates that, yes, some of the resamples truly were tougher to predict than some of the other folds or other resamples, okay? If that wasn't the case, you wouldn't really see any kind of this thing that, some would perform better or worse. You would have like kind of ups and downs all over the place, a lot of kind of crossing lines. You have a little bit of crossing lines here, but, overall we see a lot of kind of these parallel things where, these lines indicate that, these observations, whatever they were just tough to predict, and everybody kind of performed poorly on them, okay? All right, let's talk about tuning our model parameters. So not just resampling and comparing different models, but we can use tidy models to tune the models, okay? And what we mean by that is that a lot of our models have these hyperparameters that we need to choose. So, for the linear models, we specify different recipes. But for some of the other things, you might do something like k nearest neighbors, and you have to decide what k to use. Do I use a k of 3, a k of 5, a k of 10, k of 20? How many things? For the random forest model, how many trees do I want? Do I want 500 trees, 200 trees, 1,000 trees? There might be different kinds of, hyperparameters you want. Okay, if we revisit the recipe in our aims thing, right? This is our recipe. There were kind of two numbers that we chose arbitrarily. One was how many degrees of freedom for the spline, and we kind of eyeballed it and said, hey, let's use 20. And then the other was, what threshold should I use to create an other category? And we just said, hey, 1%, that sounds like a small number, and that sounds pretty good, and that's what we did. But maybe we should have used 2% or 5%. Maybe we shouldn't have used 20 degrees of freedom. Maybe we should have used 50. And I think one of the models did use 50 degrees of freedom, okay? And so what we can do instead is we can create tunable parameters, okay? And so so rather than having a number, 0.01, we put in tune. And then rather than we'll do longitude and latitude separately, okay? And the degrees of freedom, rather than just putting in the number 20, we'll put in tune, okay? And we'll give it a little name here, okay? So we have degrees of freedom tune. We're going to call it longitude df, and then we'll have degrees of freedom tune latitude df, okay? And so we will have tunable parameters here. And so this will kind of give us the ability to refit this model a whole bunch of times, and we can say, hey, try it out with degrees of freedom, 5. Try it out with degrees of freedom 20. Try it out with degrees of freedom 15. And then we could say, hey, try it out with threshold 1%. Try it out with threshold 2%. Try it out with threshold 3%. And we could try out different thresholds here, okay? And again, you could do this manually, but it's kind of a pain because you'd have to, you try out a number and then fit it and see how it goes. And then you do it again and you fit it and you see how it goes. Tidy Models says, hey, you know what? You want to try out a whole bunch of different values, tunable parameters. I got you covered here. So now that we have these different kind of tunable things, Tidy Models calls these dials. Okay, so it's kind of like imagine this big kind of control board, switchboard, where you have these little knobs, these little dials that you can kind of crank up or crank down to affect the performance of the count. Performance of the thing. So think of it like a big kind of soundboard, and you want to say, hey, I want to kind of adjust the intensity of the mid frequencies, and I want to adjust the intensity of the high frequencies or low frequencies, right? You've got these kind of equalizer things, and you want to kind of adjust some of these things to kind of improve the sound or whatever. And similar kind of thing, you want to say, hey, I want to change the degrees of freedom, right? And so here we can say, hey, look at that recipe that we created, this Ames recipe, and look for basically this thing tune, okay, that function tune, and extract out the different dials. So extract out the parameter set dials here, okay? And it says, all right, you have one, we call it the threshold, and then we have degrees of freedom things, right? So we have, because here the parameter we're tuning is degrees of freedom. And again, instead of specifying a number like 1% and 20 for degrees of freedom and threshold, we're going to make these tunable. And so the threshold, we didn't name it, so it just gets the name threshold. For the degrees of freedom, we gave it a name, longitude df and latitude df. So those have identifiers there. And it says, hey, we have 3 parameters that we're going to try tuning. And these are the default ranges that it's going to test, okay? So when you say, let's say what kind of threshold in here, it says recipes parameter, we say extract parameter dials, okay? For threshold, it's going to say, hey, we're going to try out anything from 0 to 10%, okay? For the longitude df, we're going to try out anywhere from 1 to 15 degrees of freedom, okay? And we might want to change that. And we might want to say, hey, don't go 1 to 15 degrees of freedom, go from 5 to 25 degrees of freedom. And for a threshold, instead of going from 0 to 10%, try going from 1% to 10% or something like that, right? So we can take our the parameters that we want to that we have, right? So we have these recipe parameters. We can update them, and we can say, hey, these are the ranges that we want to do. Okay, we want degrees of freedom to go from 5 to 25. All right, so that's what we have: spline degrees of freedom, threshold, right there. Okay, and so we can kind of change the range that that Tidy Models is going to search. It's going to search a new kind of range of things. Okay. You can also, so some models already have tunable parameters. So one of the models, again, I haven't covered this yet, but this could be something you might want to try out. There's an MLP model. This is a type of neural network. And one of the parameters is hidden units. So in a neural network, you have a hidden layer, and you can specify, hey, try it out with 30 nodes in the hidden layer, okay? Or you can say, hey, make that tunable. And you could do that right in the beginning when you specify the model itself. So, normally, for the other things we said, hey, I want a linear regression model and set the mode to regression and the set engine to LM. You can say, hey, I want a MLP model, and right away, before you even specify something, you can say hidden units equals tune, okay? Or random forest, when we specified random forest and we said number of trees, 1,000 or whatever, you can just throw tune right away in there, right as soon as you specify the model, okay? Set the mode, set the engine, do those things, but you can specify a tunable parameter right up front, okay? There are a whole bunch of things that can be tuned. So let me just kind of show you an example. Working with tunable parameters. So you have, so for things in regression trees or cart trees, one of the parameters is like cost complexity, and you can set basically what kind of range you want there. And so these are just an example. As far as you have other things where you want to try out, like the parameter is not a number, but the parameter is something like has a name. Okay, so for example, you have like a distance weighting function. Okay, a distance weighting function basically says, hey, values that are closer get weighted heavier, and values that are farther away get weighted less. Now, what formula do you use? You have different weighting formulas or different weighting functions, okay? So you have a rectangular weighting function. I don't remember the details of all of these things, but basically, you know, it's kind of like inverse squared law or inverse cube, or, you know, you want to have it, you know, in a linear kind of form and things like that, right? So you can also kind of set the names of some of the things that you want, right? So these are different kind of things. Here in the reference, these are basically all of the different kinds of parameters that can be tuned. So so in splines, you can have like the number of knots, other things, you know, kernel smoothness, just a whole bunch of different tunable parameter types that you can have here under dials, which is pretty nice. Okay, pretty nice. So other examples: how many nodes in a layer for a neural network, how many neighbors to use in a k-nearest neighbors. If you're doing some kind of boosted tree or neural network optimization, you can have a learning rate. How many randomly selected predictors in a tree-based model. These are all different things that can be tuned. Okay, so once we've established our model with tunable parameters, the way we're going to decide what values is done via a grid search. Okay, so a grid search kind of just specifies like kind of either randomly chosen or arbitrarily chosen values, and we'll try all of these things out, okay? So remember, we're trying out values between 1% and 10%, and then as far as our degrees of freedom, we can try out 5, 10, 15, 20, 25, and this kind of creates basically all of the different combinations here. So we have 100, we're going to do 5 levels for each of the 3 parameters. So 5 cubed gives me 125 combinations to try out. Okay, so I'm going to do threshold 1%, longitude 5 degrees of freedom, latitude 5 degrees of freedom. Threshold 3%, 5 degrees, 5 degrees. Threshold 5.5%, threshold 7.75, 0.0775, threshold 1, 10%, okay, with 5 and 5. And then I try it again. This time longitude df goes up to 10. So this is going to be a regular, evenly spaced out grid, okay? And that's one way to run it, okay? Another option is to do a random grid, okay? And I can just say, hey, I want 100 combinations and just do random combinations. And so it'll just try out random thresholds between 1% and 10%. So I have 0.0823, 0.01, 0.0749, and then random longitude DFs anywhere from 5 to 25, random latitude DFs anywhere from 5 to 25. And so, so you know, you could do kind of regularly spaced things or just kind of a randomized thing. Okay, so here I think we'll go ahead and try out the random grid here. So here I'm going to just say make a grid random, okay, size 100 here, and then we will call tune grid, okay. So we'll fit that workflow with a tuning grid. So the tune grid function is how we go about conducting a grid search. The way it works is similar to calling fit resamples, but it has additional arguments related to the grid. And so one is the grid, which is the data frame of all of the different kind of parameter combinations that we're going to try out. If you just give it an integer, the function creates a space filling design with you know, that number of candidates, or you give it the grid itself. Okay, you know, the grid. If specific parameter combinations exist, then you give it that data frame, and that gets passed in. Okay, and then you also have an argument for parameter information for basically defining the parameter ranges. or whatever. So that's going to be useful if you're going to give it basically grid integer. So we'll try it. We have our workflow, which has the Ames recipe, which again has the tunable parameters. Remember, so we specified these to be tunable parameters here in our Ames recipe. And then we add the model, and then now we are going to take that workflow and call tune grid on this. So we're going to say, all right, try it on our vfold cross validation, and then and here we're going to do size 50 random grid. Okay, our grid is going to be recipes parameters with 50 randomly chosen spaced out grids. Okay, and this takes a long time to run. Okay, it takes a long time to run because it's basically doing tenfold cross validation for each of the 50 combinations there. Okay, grid size 50. Okay, so we get tenfold cross validation, and it did it. We did it for the 50 different grids, and we have RMSE and R squared. So each of our metrics we have 100. 100, one for, 2, basically an RMSE and an R squared for each of the 50 different parameter combinations that we tried out. Okay, and we can plot. We can say create a plot of this. This is across the x-axis is basically the different latitude df going from 5 to 25, 5, 10, 15, 20, 25. So 5, 6, 7, 8, 9, 10, and then and over here for the threshold we went anywhere from 1%, 0.01, up to 10%. 1, 2, 3, 4, 5, 6, and 7. I don't know how many. Okay, I don't know how this is spaced out, but basically this is 1% over here and 10%. And so we can see as that threshold went higher than 1%, higher than really like 2%. The RMSE went up. So we can say, all right, so very kind of clearly from looking at this thing, we can see having a lower threshold results in the kind of lowest RMSE. So thresholds greater than 1%, greater than 2 or 3%, the RMSE really kind of drops off performance. Same thing with the R squared. R squared goes down. Sorry that these plots got cut off down here. The x-axis got cut off. But basically, threshold starts off at 1% going to 10% to the right. As far as the DF goes, it's hard to see, right? Hard to tell what's going on just because there's such strong correlation between the threshold, effective threshold is so strong that perhaps, perhaps the best performing DF is like, I don't know, 17, okay? But, what got ran happened when the, when the threshold thing was too high. And so, so our performance, what we're seeing plotted here, all of these things don't reflect the longitude or the latitude DF effect, but really just are basically what's happening with the threshold. So, so that's kind of what we see. So here I can just say, hey, show the best set of metrics, and right now our best set of metrics happened when threshold was 0.0137, and my longitude and latitude DF was 25 and 6. But we also had pretty good performance, when threshold was 0.0216 or 0.0162, and we can see, our RMSE was, 0.0798 around that time. And we see it when longitude DF was 5 or 25 or 21 or 17, 18, 23, 16, 14. It's really hard to tell. So, perhaps we just kind of need to try it again with threshold only like 1%. So I said the auto plot and show best showed that threshold around 1% has the best performance. And unfortunately, because that value had such a strong influence on the outcome, it's difficult to tell what the optimal parameters for latitude or longitude should be. So what we'll do is we'll run the analysis again, but this time we'll just set threshold to say 1%. Okay, so here I'm going to just change my recipe again. Now we say threshold is 1%. We'll leave longitude and latitude as tunable parameters by using tune here. We'll run through the thing. Here I'm going to say try anywhere from 5 to 25 degrees of freedom. And we will run the grid, okay? And we'll say, hey, do grid size just 30 this time. Still takes a while to run, and this is what we get, okay? And again, so with only 5 degrees of freedom, it seems like our performance isn't super great. And it seems like our best performance happens right here, around here for latitude DF. I think, what is this, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, around 14 degrees of freedom. For latitude DF is when our RMSE is the lowest. Longitude DF, I don't know. It's lowest around here. What is that? 17? 15. Wait, 5, 10, 15, 20. So around 18, 17 or 18 BF. This is like when it's lowest around here. So something around there, So we can plot and we say, hey, where do you get the best performance? And it seems like latitude DF, 14 degrees of freedom. Longitude DF, okay, I guess 18 or 19 DF seems to give the best performance. But we also have good performance when we had 13 degrees of freedom and 7. But certainly around 14 or 13 or 14 degrees of freedom for latitude seems to be having the best performance. And, longitude DF, yeah, probably 18 or 19. That seems pretty good. And so that's what we would settle on. So that is kind of how you could start comparing a bunch of models using V-fold cross-validation and using V-fold cross-validation to tune, hyperparameters for a given model. So if you have a certain model and you want to say, hey, how is this going to perform with different settings for our hyperparameters? You can use tune. You'll fit the fit it using tune grid, and try that out. Okay, so that covers up through chapter 13 in the textbook here. Okay, in the grid search, and you can see additional stuff in the textbook. Again, please do your reading, and you can see even more things in, say, chapters 14, where you have an iterative search, and you can also kind of screen a whole bunch of these different models here in chapter 15. But certainly chapters 9 through 13 will cover, how do you measure the performance of your model, and how do you make comparisons between multiple models there. Okay, I'm also working on your Kaggle competition. I have a data set that I think is interesting, and I'm just preparing it for the competition. So keep your eyes tuned for that, and I'll give you more information once it's ready to go.